Hi there, and welcome to week 2 of our weekly wrap-ups, where I will just quickly go through the chemistry that we need to know by the end of week 2. This is what we were doing in the class. So broadly, there are about 3 main areas that we need to consider. The first one that we looked at was the way that we represent our organic structures. And you can go and read in your textbook the different ways, but essentially what we want to get to is the way where we are able to look at what we generally call the skeletal structure of molecules, which would look something along these lines. This is effectively just a line drawing, all right, where we just show lines between the bonds between carbon and between carbon atoms, and we don't show the hydrogen atoms except if a hydrogen is on a heteroatom. All right, well, this structure that I've drawn over there, its common name is Skeletal. It is the smell of poo. All right, stinking pile of poo. It actually arises out of the decomposition of, or the breakdown of the amino acid tryptophan, which is found a lot in meat products, and so animals that eat a lot of meat have the smell of poo. And anyway, tryptophan, when we draw something like this, what you need to be able to do with looking at structures like this is to very quickly see where the carbons are and to see where the hydrogens are, which are hidden. And so if you look at a structure like this very quickly, I should hope that you'll be able to work out its molecular formula, the number of carbons, the number of hydrogens, and in this case, we've got nitrogen as well. And so we can count these up. Carbon, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm hoping that is now easy for you. And hydrogens, we've got 1 there, 2, 3, 4, 5, nothing there, 6, 7, 8, 9, and nothing there either. So the molecular formula is C9H9N. Okay, so it's important that you make sure that you are able to look now at skeletal structures, that you're able to draw them neatly. Remember, I went through that in class. Just trying to stress exactly just some of the good techniques that we have in drawing out these structures. Also, you should be able to immediately recognize that nitrogen has a lone pair of electrons, that there are 4 pi bonds over there, that you can recognize all the sigma bonds in the molecule, including between the nitrogen and the hydrogen, and the hydrogens over there, all the hidden hydrogens as well, sigma bonds. Okay, so that's really about the most difficult in terms of just interpreting those sorts of structures. Now I want to deal with something else which we briefly touched on and we'll continue to touch on, and it's the concept of resonance. I know that this is a very, very, very difficult thing for you to grasp, but what we're going to do is we're going to continue to do lots of examples, and hopefully something is going to sink in. Eventually you're going to start to look at these things and say, okay, I understand, I can see where all the electrons are and how we move electrons in resonance. So I'll draw this structure up over here. I've actually drawn the hydrogens in because I just want to be sort of explicit about that. I want to show exactly where they are. I've left the carbons out, but don't be confused by that. Okay, make sure that you understand that there are 3 carbons there. Now this molecule has a negative charge on the oxygen. It has a carbon-carbon double bond. It has a carbon-carbon single bond. And then this oxygen over here has a double bond onto it. And then the hydrogens are obviously just single bonds because hydrogen can only have 1 bond to it. Now for resonance, if we had to draw out a resonance structure of this, we can do this because where the negative charge is, if we move it in like this to form a double bond over there, it's next door to a carbon, all right? This oxygen is on a carbon that already has a pi bond on it. So although this carbon's got 1, 2, 3, 4 bonds to it, and when we push that in, it's going to get another bond, it won't have 5 anymore because this pi bond can break and end up on that carbon atom over there. If we draw that out, remember we use the special arrows only ever used when we do resonance, and the product will look now like this. It actually looks a whole lot more symmetrical. There's a hydrogen there and a minus charge on that carbon over there. All right, so hopefully you could see how that moves. Now remember, again, resonance is only movement of electrons from lone pairs or negative charges and on pi bonds, but it cannot just jump across. All right, the negative charge doesn't go boom from there to there. All right, the negative charge, it's like dominoes. It goes in, forms a new bond there, then this bond breaks. Atom, atom, atom. From this atom to that atom, from between those two atoms, breaking onto that atom. All right, it's only going between the two atoms. All right, and we can actually do this again. The negative charge can move again. It can bounce in like this to form a pi bond here, which it can do because this pi bond can break from the oxygen. And what we're left with is a molecule that looks like this. All right, I'm going to space there. So this, all right, looks exactly the same as that one. All right, it's just like a mirror image almost of it. And what this shows us is that the negative charge on this oxygen also can exist on this oxygen, and it also can exist on this carbon over here. And so this whole lot in between gives us almost like a snapshot of the three places that the minus charge can sit on this molecule. And it's allowed to sit through resonance. The negative charge is delocalized onto the oxygen, this carbon, and this oxygen over there. And what we can do, and I haven't shown this in class yet, is we can actually redraw this whole structure with just the sigma bonds intact. And you see that over this whole structure, it's like we can form a pi bond there. There's a pi bond here. There's also a pi bond over here. And there are pi bonds over there. It's kind of like the pi bond is extended over this whole structure, and the minus charge is delocalized over these two oxygens and this carbon over there. All right. Hopefully that helps a little bit, but we will do more examples of resonance, so don't be too worried about that. And then the last thing that we did is we looked at naming of compounds. We've just started this, and this is also very important. We need to be able to name compounds, and I've stressed to you the most important thing is being able to, if I give you a name, and so I'm going to do this, 3-ethyl, 2,5-dimethyl heptane. Okay, I want you to pause the video and I want you to try this. Please, it's a good thing. I will stress this over and over again. It is a good thing for you to try this for yourself first and then see if you got it right. And you can then watch me do it and see whether you did it correctly or where your mistakes are, and then to learn from your mistakes. It is a good thing. All right, so pause the video now. And now I will start to draw this out. Okay, so we must quickly identify that the parent, all right, the longest chain in this structure is heptane. So we draw out our zigzags, all right? So I drew out my zigzags. Actually, those are horrible. So I get rid of that. All right, let's do that a bit neater. All right, there we go. All right, 1, 2, 3, 4, 5, 6, 7. I drew too many, so take that out. All right, okay. 1, 2, 3, 4, 5, 6, 7. Can be a good idea actually to number your carbons. All right, there we go. 7 carbons. Maybe you can't see that, but anyway, they're numbered. And now what we need to do is we need to put an ethyl group on carbon number 3. There's carbon number 3. So carbon number 3 is bonded to an ethyl group. Carbon number 3 has a bond to an ethyl group, which is 2 carbons. All right? Did you get that? And then we've got a methyl group, but we've got 2 of them on carbons 2 and 5. So there's carbon 2. There's a bond to 1 carbon atom. All right? 1 bond to 1 carbon atom. And then on position 5, we have another carbon atom over there. And so this would be the correct structure. Now please be careful. Now don't get worried if you've drawn out the structure differently. Like for instance, I went zigzag, zigzag. Maybe you went zag, zig, zag, zig. All right? That's okay. Just check that the principle that you followed is exactly the same. All right. Try and draw your molecules nice and neatly. Get 120-degree angles between the bonds. Try and keep your bonds all the same length just to have it nice and neat. And this will help you later on. And then the last thing I did in the lecture was actually to point out to you that there were, of the substituents, ethyl, methyl, propyl, butyl, these are very simple substituents, but that the propyl and butyl substituents also had some isomers which had different names. And one of them, for instance, was the isopropyl group, which is something that looks a bit like that. All right? And we also looked at the different butyl substituents. All right? That was N-butyl. This was S-butyl. Then we had the T-butyl, which is connected to the center over there. All right, T-butyl. And then we also had the isobutyl, which was connected over there. All right, notice as substituents, 1, 2, 3, 4 carbons onto the chain. 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 All of these are butyl type groups. Butyl, sec-butyl, tertiary butyl, and isobutyl. This one over here looks like an isopropyl if this over here was the longest chain, right? Which is 1, 2, 3, 4, 5, 6, 7. It's also 7 carbons. There's a very good reason, this is part of the IUPAC rules, that we don't actually consider this to be the longest chain. But that's very complicated and we don't need to know that. All right, I want to stress, I want you to be able to draw out a structure from the name. Don't worry too much about generating a name from the structure. We just use computers to do that ourselves. All right. So hopefully that settles everything. Just with the T-butyl group, if we're going to draw it out, it's possibly just draw it a bit neater. We want to do it like that. All right. Anyway, hope you enjoy.